Yep, that seems to have worked. So, hello everyone, and thank you for joining this lunchtime event organized by Young Saked to celebrate the Women in Engineering Day, which is later this week. We have invited today 3 young, talented women who currently work in the field of earthquake engineering, and they will talk to us about earthquake early warning systems. But before I introduce our speakers, please let me go through a few housekeeping rules. Please can everyone keep their videos off and microphones on mute during the seminar. We will have a Q&A session after all 3 presentations, but please feel free to type your questions in the chat at any point. Please note that this seminar is being recorded and will be uploaded onto our YouTube channel. Therefore, by dialing into this event, you consent that any views or opinions you share being made public. So, moving on. In this event, we have with us Gemma Cremen, Laure, Fallou, and Irina Dallo, who will cover both technical and social aspects of earthquake early warning systems. Gemma received her PhD in earthquake engineering at Stanford in 2019. Following postdoctoral work in seismic hazard and risk analysis at the University of Bristol and at UCL, she became Assistant Professor of Risk and Resilience Engineering at UCL in 2021. Her research develops risk-informed decision support tools for various natural hazards. Laure is a research officer at the Euro-Mediterranean Seismological Center. With a background in sociology, she has been studying over the past 5 years how cultural factors impact citizens' reactions to earthquake risk and more recently to earthquake early warning systems. Committed to seismic risk reduction, her research includes risk communication and places citizens at the center, notably through citizen seismology. And last but not least, Irina Dallo is an environmental scientist and holds a Doctor of Sciences from ETH Zurich. Currently, she is a postdoctoral associate at the Swiss Seismological Service, working on how to best communicate hazard and risk information to the society and how to strengthen transdisciplinary research. So, I think the profiles of our speakers speak for themselves. So without further delay, I will hand over to Gemma for the first presentation.
Thanks a lot, Tina. I'm just gonna share my screen. I'm not the best with Teams, so just give me a second, sorry.
It's the trickiest part always.
Is it in full screen
Yep.
mode? Okay, great.
Perfect.
Okay, great. Thanks a lot. Yeah, so thanks everyone for coming along. As Tina mentioned, my name is Gemma Cremen, and I am a lecturer in risk and resilience engineering at UCL. So today I'm going to talk about towards next generation tools for impact-based early warning. And I carried out this research funded by the Turnkey project, which is a Horizon 2020 funded project. So I just want to acknowledge them. And a lot of the work that I carried out within this research project was also done in collaboration with Professor Carmine Galosso at UCL. So before I get into the main kind of research that's going to be presented in this talk, I just want to start off with a little bit of an introduction to the concept of earthquake early warning itself. What exactly is earthquake early warning? So a formal definition of earthquake early warning would be, it's a set of sensors and mathematical tools or algorithms that are used to process and disseminate information about ongoing earthquakes in real time. So what happens is we have a rupture, and the first type of P waves or waves to emanate from an earthquake rupture would be P waves. And what happens in an earthquake early warning system is we have a set of seismic sensors that are set up located close to possible epicentral areas. They detect these incoming P waves. And then we use a set of methods, models, or algorithms to translate the information provided by the P waves into estimated characteristics about the incoming earthquake, such as its potential or estimated location, for instance, its estimated magnitude, and we can then go further and actually calculate its estimated ground shaking intensity in space using, for instance, a ground motion model. And we would call this type of approach network or a regional earthquake early warning approach. We also have another type of approach where we just have one seismic sensor located close to a particular critical infrastructure of interest, like a hospital or school, for instance. And in that case, we take the information coming from the detected P waves and translate it directly into ground shaking estimates at the critical infrastructure location of interest using different types of models or algorithms. And we call this a single station or on-site earthquake early warning approach. Now, regardless of the approach that we take, the last step in an earthquake early warning system always will be a decision-making process. We need to decide whether or not to issue an alert before the stronger S waves from the incoming earthquake actually hit locations of interest. Now, this is an important step because we can't always issue the alert for every earthquake we detect, because most of the earthquakes will be too small to have any kind of appreciable effect on people's everyday lives, and we can't always be causing them unnecessary disruption. So we need to make sure that our decision-making approach on whether or not to issue an earthquake early warning alert for an incoming earthquake is calibrated correctly. Now, if we do issue an earthquake early warning alert, there's typically on the order of seconds to tens of seconds to take rapid risk mitigation actions before the strong S wave shaking from the earthquake actually hits people's locations. So the types of rapid risk mitigation actions we can take within that time frame include ducking, covering, and holding under tables or chairs, for instance, to prevent casualties. We could stop vehicles from entering bridges. We can slow down trains to prevent derailments. And if there is enough time, we can even consider potentially evacuating at least part of the ground floor of a building, for instance. Back in 2020, I conducted a review of existing earthquake early warning systems around the world, and I found that there was around 9 in operation and around 13 or so in testing. So, for instance, we have the United States Geological Survey in charge of the Shake Alert system on the west coast of the US. We have projects like the Turnkey Project, which this research was funded under, looking at the possibility of having operational earthquake early warning in Europe. And we have the Japan Meteorological Agency, for instance, in charge of earthquake early warning in that country. Let's move on then to kind of the main topic of today's presentation, which is calculating earthquake early warning feasibility across Europe. Or in other words, how potentially beneficial would earthquake early warning be in the continent? And to answer this question, we focus on one of the first steps in earthquake early warning in particular, looking at where seismic stations are located and how they can detect incoming earthquakes. So the first thing is we decided and identified high hazard seismic sources across Europe, and these are shown on the right-hand side in the map. We then determined how fast P waves and S waves emanated from those high hazard area sources across Europe. And we finally identified seismic station locations across Europe. We then combined all of that information together to produce what we call a lead time map. Now, what this lead time map tells us is the amount of time people would have to take risk mitigation actions between when an earthquake early warning alert is issued and when the strong S-wave shaking from the earthquake actually hits their location of interest, their target sites. So the higher the amount of lead time we have at a particular target site, the more opportunity there is to take rapid risk mitigation actions when an alert is issued, and therefore the more potential there is for earthquake early warning to have a beneficial impact. Now, this is just one lead time map I'm showing for one high hazard area source affecting a given target site. But in reality, each target site will be affected by a number of high hazard area sources around it. So what we did is we iterated across each high hazard area source for each target site, calculated the lead time associated with each area source for each target site, and we were then able to come up with a lead time distribution for each target site. So all of the possible lead times it might have if an earthquake early warning system were to be installed for that target site. Then we can derive a number of different maps from that lead time distribution. We have a minimum lead time map, or a worst case scenario, the least amount of lead time a target site would have for all of the high hazard area sources around it, all the way up to a maximum lead time map, or a best case scenario, the most amount of time each target site would have in terms of lead times for high hazard area sources around it. So if we focus on the bottom right hand map in particular, so this maximum or best case scenario, what we found was that around half of the target sites would benefit from at least 5 seconds of lead time in a best case scenario. Now, this 5 seconds of lead time would give us the possibility of taking risk mitigation actions like ducking, covering and holding, for instance, turning off gas supplies, even evacuating some of the ground floor of a building, for instance. And you can see that a lot of that map is coloured, which means that there's a lot of positive lead time for target sites across Europe in a best case scenario. Now, of course, this is dependent on the magnitudes of the incoming earthquakes, as well as the threshold which we use to issue an alert. However, this is a positive indicator for the potential beneficial impact of earthquake early warning across Europe. There is lead time available for an earthquake early warning system to be effective. Now, this is where a conventional feasibility study would normally end. But lead time isn't really the whole story. It doesn't give us the whole idea of how beneficial an earthquake early warning system would be. For that, we also need to know where people live in relation to where there is a high amount of lead time available if an early warning system was to be installed. And we also need to understand the average seismic intensities affecting target sites with high amounts of lead time. Now, you'll often see, and I've reviewed a number of publications for peer-reviewed journals that will advertise really high amounts of lead time for an earthquake early warning system that they're considering, but these lead times will be located, 200 to 300 kilometers away from magnitude 5 earthquake sources. And at that distance, there's no real point in having an earthquake early warning system. Yes, you'll have a lot of time to take risk mitigation actions, but there won't really be any risk to mitigate in that case because the shaking will be so low. So by combining our lead time calculations with information on population or exposure, as well as average seismic intensities experienced, we can have a more informed view of how potentially beneficial earthquake early warning would be across Europe. So this is what we did. And when we combined all the information together, we came up with plots that look like this. So we have examined population on the y-axis as a function of different potential lead times they're exposed to. And we also have the average seismic intensities that these examined populations are exposed to from nearby high hazard area sources. So what we can do is, if we add up the y-axis of both these plots, we'll see that around 98% of the examined population are exposed to average seismic intensities between strong and damaging. And this is a good sign. This means that there is risk to mitigate if we did install an earthquake early warning system. And then we need to superimpose on top of that lead time information. How much time is there available to mitigate this significant risk? So we can see if we focus on the maximum lead time bar in particular, there's a lot of color on this bar, and this means that there is positive lead time available. So in all, we can conclude that a notable proportion of the population has positive median and maximum lead time for relatively large intensities. So this is kind of validating our lead time calculations in the sense that we have a further positive indicator for the potential beneficial impacts of earthquake early warning across Europe, considering risk as well as just lead time. Now, what we did is we synthesized all this information into a quantitative metric, which we termed a relative feasibility index, which contains those three components: lead time, population, and average seismic intensity. Now, this is a relative feasibility index. So what we're doing is we're measuring the feasibility for earthquake early warning at a particular target site relative to all other target sites that we examined. So the maximum value for this index would be 1, and this would be for a target site that had the highest amount of population around it, was exposed to the highest average seismic intensities, and had the highest amount of median lead time associated with it. So the larger the value of the index, the more feasible earthquake early warning is at a particular target site. Now, an interesting feature that we included in this index is that we weighted each of the different components of the index to account for diverse stakeholder priorities on decision making when it comes to earthquake early warning. Because we might imagine, that one stakeholder is more interested in installing earthquake early warning in an area where there's a high amount of population, whereas somebody else might be more concerned with the amount of lead time that's available for an early warning system. And we can account for these preferences by weighting the different components of the index differently. So we're now going to assume that all of the different components are weighted equally, and we calculate the relative feasibility index for target sites across Europe that have positive median lead time. And we see that if we focus on the green triangles shown in this map in particular, that earthquake early warning is most feasible for Italy, Turkey, and Greece. Now, this is a particularly notable finding for Italy and Greece in particular, because neither of these countries have currently government-supported operational earthquake early warning systems in place. So to conclude, we found that around half of target sites could benefit from at least 5 seconds of lead time in a best case scenario, again, depending on the magnitudes of the earthquakes, as well as the threshold used to issue an alert. But nonetheless, this is a positive indicator for the potential of earthquake early warning across Europe. And we further validated that by providing estimates of population and seismic intensity on top of this lead time calculation. So in all, we can conclude that earthquake early warning would be useful as a risk mitigation measure in Europe, but importantly, as a supplemental tool. Now, this is a really important term because earthquake early warning can't solve all of our seismic risk issues by itself. If we install earthquake early warning in a building that ends up collapsing in an earthquake, then that earthquake early warning system would have had no beneficial impact in terms of, for example, reducing casualties. So we need to make sure that we have good building code provisions and other types of risk mitigation measures in place, as well as earthquake early warning. And earthquake early warning will operate effectively as part of a suite of risk mitigation measures. And finally, we saw on the last slide that earthquake early warning is most beneficial for Italy, Turkey, and Greece. So we recently had this published in Nature Communications, and we had some media attention as a result, again, because both Italy and Greece don't have operational earthquake early warning systems that are government supported, and Turkey only has an earthquake early warning system around the Istanbul area. So thank you very much for listening.
Brilliant. Many thanks for both the introduction you provided, Gemma, at the beginning, and the summary of your work. I appreciate it's tough to summarize your work in 10 minutes, but thank you for that. Before we give the floor to Laure, a reminder to our audience, you can place your questions in the chat at any point and we will address them at the end of the 3 presentations. So Laure, over to you. I think you are muted. We cannot hear you. I don't think so. Would you like us to swap the presentations and leave Irina give hers first and we sort that out? So minor change of plans. Irina, we will put you on the spotlight a bit earlier than expected.
That's fine. I'm just sharing my screen now.
Okay, all perfect.
Okay, so welcome also from my side and thanks for inviting me. I'm Irina Dallo, a postdoctoral researcher at the Swiss Seismological Service. And in the next 10 minutes, I will present you the Swiss case study where we focused on the social perspective of earthquake early warning systems. The study was a joint effort between the communication team, so Michel Marty, Simon Zaug and myself, and the technical team, John Clinton, Madame Böse and Frédéric Massin. Before I start with presenting you the study, I would like to start with a question. Why does the societal perspective matter? Here I listed 3 reasons, but of course there are many more. So the first reason is that studies have shown that the design of messages affects whether people take actions or not. So with different information elements, you can motivate people more to take actions or less, and also to motivate them to take informed decisions. The second reason is that the technical settings, so the defining the thresholds, should be based on people's needs, because only if the system works how they expect it works, they actually will also use it and are happy with it. And third, people's concerns and misconceptions should be better understood, and by assessing them, you can then tailor your communication campaigns, training efforts to the specific concerns and misconceptions to make sure that the public or other stakeholders of the society actually understand how the system works and have not false conceptions. So with this introduction, I would now like to dive into the study. And for the study, we use the transdisciplinary research approach. And what does transdisciplinary research is? Transdisciplinary research is at the intersection between science and society. So we do not only collaborate with scientists from different disciplines, but we also involve the stakeholders of the society to test certain products. In this specific study, we first looked at other countries, but how do they communicate the earthquake early warning system to the public? How do the warnings look like? And then based on that, we conducted 65 virtual and in-person semi-structured interviews with the public in Italy, Iceland, and Switzerland. And this was part of the Horizon 2020 project RISE. And there, in these interviews, we showed them certain messages, for example, the ones that the shake alerts sends, or the Mexico ones, the ones in Japan, and gather people's first impression regarding these messages. Based on the insights, we then designed different earthquake early warning messages for Switzerland, and together with the scientists at the Swiss Seismological Service, we refined them and make sure that the technical possibilities really cover the messages. And then with a between subject experiment, we tested these different earthquake early warning messages with the public to understand which messages are best understood and which ones triggers them to take action. In this survey, we also assessed people's general preferences regarding the earthquake early warning systems, and also their concerns or the acceptance of technical limitations. And I will now present you the main insights, and we'll start with the general attribute preferences, concerns, and technical limitations. and then go further to the earthquake early warning message designs. So regarding the channel preferences, 66% of the participants prefer to receive earthquake early warnings for felt earthquakes, so not only for damaging, but for all earthquakes that they may feel. Then the majority would prefer a warning time of 20 or more seconds, which is technically not possible in Switzerland, but this is the general preference people have in Switzerland. Then 68% prefer to receive the warning as a push notification or also as a public notification, for example, in the shopping mall or television, but the majority prefers to receive a push notification. Then we also asked them whether they think they know how an earthquake early warning system works, and about 90% said that yes, they know it, and then they had to describe with their own words how they think it works. And there we identified several misconceptions, so they do not actually know how it works, but they think that they know. And these misconceptions are, for example, that they think earthquake early warning systems are a prediction, or that deep sensors deep in the ground detect the earthquake and then send signal to the surveys. So we have several misconceptions which could then be addressed in an information campaign. Regarding the technical limitations, so we asked them about their acceptance of these limitations, and more accepted are second messages with more accurate information, and also that the information has to be updated after several minutes or hours. Less accepted are false alerts or late alerts. Regarding their concerns, so the majority thinks that they have not enough time to react, that no one around them will take any actions, and the further reason is also that they do not know what to do in the specific situation, and therefore they won't take any actions. And the last one, nothing happened the last time, therefore they would not do anything when they receive a future alert. With that, I will now come to the earthquake early warning message designs. As you can see here, we have tested 6 different versions, and we specifically varied whether it's a visual format here on the left or an audio message. So the audio message, they just listen to an audio message, and when they saw a visual, they really saw this prototype, as you can see it on the left. Then we had some for weak shaking with the green color and for strong shaking with the red color. Then we had some messages with a map as the main information element, and on the right you can see with pictograms as the main information element. And then further, to some participants, we only shown the message for 3 seconds and for the others for 5 seconds. And then afterwards they had to answer 2 questions. And the first questions we asked them was, which action would you now take when you received this earthquake early warning message? And as you can see, most of them would warn or protect others, which is also in line with other studies that looked at the societal perspectives of earthquake early warning systems. Then they would also protect themselves on the spot. I think here the people were too optimistic compared to real-world testing. Or they would also move nearby to where they think it's safe. And now, which effect does the warning designs had on these first intentions to take actions? So we have seen that the message with pictograms triggers participants more to protect themselves directly on the spot compared to do nothing. Also, the messages for strong shaking motivates them more to protect themselves on the spot or to move nearby where they think it's safe. So here it was a nice insight that participants reacted or would react proportionally to the shaking intensity. Also, the participants who listened to the audio message were more likely to protect themselves on the spot or to mentally prepare themselves. We also then asked them which information they recalled on the message, and on average they recalled 3 out of 6 information elements. And one important insight for us was that the information at the bottom of the message was less recalled. So here this gray information, report an earthquake or more information, was less recalled, which is good because we wanted them to focus on really the red highlighted information or the map or the pictograms, and the information at the bottom is then for the second action when they want to report the earthquake or get more information. And the further insight here was that the weak shaking was interpreted as strong shaking, even though it was written that it's only weak shaking and warning earthquake and the green color, but the pictograms led them to think that it's for strong shaking. And then the last question of the survey was whether they would prefer an earthquake early warning message with a map or pictograms. And here you can see that 75% prefer an earthquake early warning with a map. However, as we have seen before, the messages with the pictograms triggers people more to take action. So here the conclusion is that the generally preferred versions are not always those that actually trigger people to take action. So you have to find a balance between preferences and actual information elements that help people to take action. And with that, I'm coming to the overall conclusion. So the Swiss public wants to receive earthquake early warning messages. As we have seen, the message design matters because with different elements, you can already have a significant effect of people's intention to take action. Then we have identified several misconceptions which would or have to be addressed when Switzerland decides to have an earthquake early warning system. And all these insights we were only able to gain these insights through a transdisciplinary research approach, because this allowed us to collaborate with scientists from different disciplines to understand also the technical limitations or restrictions, but also to test these messages with the public to get their needs and concerns. And therefore, I motivate also others to use transdisciplinary research to get the societal perspective. And with that, thank you very much for your attention, and I'm looking forward to the discussion, or if you have afterwards any questions, please do not hesitate to contact me.
Many thanks for your presentation, Irina, and I think the audience must have enjoyed that a lot. Without any delay, I'll hand over to Laure.
Hi, is it working now?
Yes, all perfect.
Good, perfect. Sorry about that. So I'm going to share my screen. Where is it? There. And I'm going to start now. Yes, is that working? Yes.
Yes, it does.
Okay, so hello everyone, I'm Laure Fallou and I'm a research officer at the EMSC. And in this presentation, I'm going to focus on how people actually react to earthquake early warnings when they receive one. This first research has been supported by both RISE and Turnkey, which were mentioned by Irina and Gemma, so it's kind of a collaboration. So to start, I would like you to take 1 or 2 seconds to wonder what would you do if you received such a warning. So if you received a message that says earthquake in 5 seconds, what would you do? This is an interesting question because often there might be a difference between what people think they would do and what is their actual reaction. So of course it is very important to study intentions to design the systems, but it's also very important to study actual reactions to improve the systems. So in our study, we focused on Earthquake Network, which is an app that provides an earthquake early warnings service. The system uses the smartphone's accelerometers to detect in real time the shaking induced by an earthquake. I'm not going to focus on the technical aspects of this system. You can read the paper that is cited as reference here if you want to know more. But I think what is important is to give you a small words about how the warning works. So it is composed of a very simple message, a specific sound. So we also have like the alert as a sound. We also have a countdown and a map. But what is specific of this earthquake early warning system is that it is voluntary and it is community-based. So voluntary because people have to download the app to receive the alerts, and community-based because the more people download the app, the more efficient the system. So in our survey, we took the example of a magnitude 8 earthquake that happened in Peru in 2019. The earthquake happened at night and was largely felt in several countries, but mainly in Peru. So for this earthquake, the EQN system launched a warning to some of its users that were potentially affected by the earthquake. And we decided to launch a questionnaire among the EQN user in the area to know what were their experience, how they understood and perceived the alert, but also how they reacted to it. So in total, we collected 2,625 answers, which is quite a large number of answers. So we were pretty happy about the sample we collected. And I'm going to detail a bit more about what we learned through this survey. So first of all, we saw that there is a very high level of interest for earthquake early warning. So a bit like Irina said, for Swiss people, this was the same in Peru. And it's even the first reason to download the app. Another fun fact that kind of illustrates the will to get earthquake early warning is that a seismologist reported to us that people started buying Android smartphones to replace their Apple after the earthquake because at the time the app was not available on iOS, so they wanted the app so bad and the earthquake early warning so bad that they were ready to change their smartphone. When we started the questionnaire, we had no way to know exactly who had received the warning and for whom it worked. So we asked the participant to tell us whether they felt the earthquake or not, and whether they received the warning, and if yes, was it before or after the shaking. And with that, we found that the warning worked perfectly well for 41% of the respondents, either because they received the warning in advance of feeling the earthquakes or because they didn't receive it and didn't feel the earthquake. So there is still a significant share of the respondents who experienced missed, false, or late alerts. We're going to focus here on those 34% of respondents who received the warning before feeling the earthquake. So 79% of them understood correctly the message, which is a positive result when we know how important it is that a warning is understood to be efficient. And on the whole, a majority of the respondents felt alerted rather than anxious, which is also a positive result because we don't want to scare out people, just alert them. And when we looked a bit more in details, we found that those who didn't understand the notification felt proportionally more confused than others. And also experience matters because having previously received other earthquake early warning notification for past earthquakes raised the probability both to understand and to stay calm when receiving the warning. But so what really matters here is what people actually did after the warning. So we often hope that earthquake early warning will enable the public to drop cover and hold on, or to put themselves in a safe place. But that was actually not the case for this earthquake. So only a quarter of the respondents did so, which is kind of consistent with Nakayashi findings on how the public mentally prepares thanks to earthquake early warning rather than to drop cover and hold on action. So this is here represented by the I waited for the first vibration option. But despite the fact that they didn't drop cover and hold on, still 75% of the respondents declared that the warning was useful. So mental preparation is really valued by the respondents. And another result that may be of interest is that understanding the notification was found to significantly increase the chances to take effective action. But what really surprised us here was that with the social dimension of the warning, and how the most common reaction that you can see on the top of the chart is to one other, whether they are physically present or not. We'll probably need more research to understand to what extent this is linked to the fact that this is a voluntary system. That is to say, not everyone has it, so it's not a universal warning. But then I also saw that in Irina's presentation, this is also a very cited option to warn others. So we'll need more studies on that. I'm just going to say a very brief word on users' perception on false and late alerts. So for late alerts, EQN users who were in this situation declared mixed feelings. For some of them, the notification added to the anxiety as they thought another earthquake was going to hit. But an equivalent share declared, on the contrary, that they felt relieved that information helped them decrease the anxiety level. For false alerts, half of them declared a high level of confidence in the fact that the system will function for future earthquakes. And what is interesting is among the other responses, many EQN users explained that they were probably too far from the system for the system to function well, or that they had changed their app parameters so that they couldn't get the alert. So these results tend to confirm findings from Allen et al. In 2018 that there is a general acceptance for the technical limitation of earthquake early warning system, and that users are more tolerant of unnecessary alerts than of missed alerts. So as a conclusion, I think it is very important to highlight that the system is still useful to the users, at least that's what they said, even though most of them didn't take protective actions. So EQN clearly meets their need, especially where no public earthquake early warning system exists in the country. And if most of the respondents did take a protective action, they still think it's useful and they got the chance to mentally prepare it. Even though the social dimension of the alert may actually be a limit to EQN early warning for now, as people want their relative to be warned also. And that kind of questions the importance of the state in this, and in the fact that earthquake early warning maybe should be a public service that should be available to us, not only because it's more fair, but also because it would be more efficient. And this has actually been expressed by EQN users in one of the questions, and they declared for at least 54% of them declare that they think it should be a state responsibility to run such alerts. And these results also show that we should probably reflect more on earthquake early warning efficiency criteria to better include mental preparation that looks very important to the users. So if you want to know more, there we go. If you want to know more about these results, you can check that paper in SRL 2022. And with that, I thank you very much for your attention, and please feel free to ask questions.
Many thanks, Laure, for all the insights you shared, actually capturing so many people's opinions, very valuable. Before we open the floor to questions, I would like to thank all our speakers for taking the time to be here with us today and present their work at Young SACED. So Gemma, Irina and Laure, a big thank you from all of us. I don't see any questions so far in the chat. Okay, first one has come. So we encourage people to put their questions. Alternatively, they can unmute themselves. You can find the unmute button on the top right part of your screen, and then you can ask the question yourself. I think the first question is for Laure. Thank you very much for the interesting presentations. It would be great for Laure and Irina if they would compare the results, particularly in the light of Gemma's findings of how such systems may be useful in Greece and Italy. I don't know who can start, Laure or Irina, but I had a similar question. If you have observed any differences between the people in Switzerland and in Peru, particularly because of the different awareness level they might have?
I don't know if you maybe I start and Irina, you can complete. I think there are of course we need to, I mean, we could compare in some extent like how people reacted with versus how they kind of think they would react, but the risk is not exactly the same in Peru, and I think they are much more used to earthquakes in Peru than they are in Switzerland. So I think we should take that into account, which is not very easy to kind of measure to what extent that impacts both their intention and their actions. So yeah, that I think that would be, the comparison would be much easier if that was at least in the same country. And also the systems are a bit different, so we should take that also into account, I think. Don't know if Irina, if you want to complete that.
Yeah, I totally agree with what you just said. So it really depends on the hazard in the country, and also in Japan and in the US, similar, or in New Zealand too, similar surveys are conducted, and the results are actually quite in line, so that people really first want or mentally prepare for the shaking or warn others, compared to take drop cover and hold on, for example. So these results is quite in line over all these 5 countries.
Thank you for that. The question from me, if I'm allowed, for Irina, what do you think is the awareness level of people in Switzerland? Because we can expect people in Peru or Italy and Greece to be much more prepared from a very young age for an earthquake, but how did people respond to the earthquake hazards? What's your feeling?
Yeah, so the awareness in Switzerland is quite low. Except of one canton, Valais. There we have quite a lot of earthquakes, low magnitude, of course, but there they also have trainings at school. They know that they have to drop cover and hold on. But in the other parts of Switzerland, the awareness is quite low. They know it from media reports about earthquakes in other countries, but about the earthquake hazard in Switzerland, it's lower, and therefore it would also be more effort needed to introduce such an earthquake early warning system, because first you have to raise the awareness about the hazard, and then you also have to explain how the system works and what they actually have to do.
Interesting. One more question from me. Laure, you said at the end the need to have a public system. So that was a question in the questionnaire. How is the system currently in Peru? Is it privatized or a governmental one?
Okay, so for the moment, there's no public earthquake early warning system in Peru. So this whole study is based on AQN, which is an app which is available all over the globe, and it works everywhere as long as there are enough people, users in the area. So that works very well in Peru because there are a lot of users. It probably works less in countries where there are less users. But so for the moment, and this is very special about the earthquake early warning. This earthquake early warning system, it is, you have to download the app, so it's not public, and I think that really matters for the results and how we can interpret them. Yeah, I don't know if that was clear.
Yeah, many thanks for that. There is another question in the chat from Sarah again. Another question from me, if I'm allowed. Yeah, just would be interested to know what Gemma's recommendation would be for an early warning system for a specific client-owned site.
Yeah, thanks a lot, Sarah, for that. It's a really interesting question, and I really like it because it's like exactly what we're trying to do, I guess, in our research, which is when we look at specific pieces of infrastructure or structures of interest at a particular site, what we're kind of advocating for is that when we're designing a system, we don't just consider the seismological characteristics of the incoming earthquakes, which is what is tended to be done in a regional system. But we actually also take into consideration the engineering aspects of that structure. So we combine the seismological characteristics with engineering models so that we can come up with a more informed idea of the effect of the earthquake on the built environment. And then we can make a more informed decision on whether or not an alert should be issued for the incoming earthquake. So we're not trying to make a decision based on some sort of like magnitude or ground shaking parameter. We can actually make a decision based on some sort of estimate of the damage it might cause or the casualties it might cause. So that's what I would advocate for in an on-site system. And then I think if it's an on-site system, you can use very detailed engineering models of the systems that you have, whereas it's not as feasible for like a city or region-wide approach, because then you need, it may not be feasible to model everything to such a level of detail that you have all your structures, all your infrastructure. But you could have some sort of proxy or some sort of archetypes that you kind of assign to each of the buildings within your system to come up with some sort of maybe lower resolution of vulnerability information that you could combine with your seismological characteristics and integrate engineering models that way. But yeah, that would be the one kind of main advancement I think should be made for on-site, very critical infrastructure applications of early warning.
Many thanks for the detailed response, Gemma. One last opportunity for questions, and I can see one from Ashana. Can I ask the basic requirements at country level, in your opinion, if we wish to extend such early warning systems to developing countries such as India, considering the size of population, regional geographic diversity, area, and the level of accessibility to technology? Very interesting one. And I think all the speakers can provide an answer. I don't know who would like to be first. Perhaps Gemma?
Yeah, sure. So thanks, Ashana. That's an interesting question. Again, I think for developing countries, so I think Laure and Irina went through some kind of strategies for having smartphone systems, which is great. And I think, smartphones are becoming more affordable. But even if we don't have kind of a smartphone-based system, we can still have a traditional regional system that doesn't depend on everybody owning a piece of their own, a phone or a piece of IT. And I think the beauty of the seismic sensors in particular is they're becoming cheaper and cheaper to manufacture, and we can use cheaper and cheaper seismic sensors to actually use in an earthquake early warning system. So this whole idea of earthquake early warning is becoming more, I think, accessible to developing countries. And regions like Peru, for instance, that Laure discussed, they're having their own kind of government-backed early warning system. They're implementing that now as well. So it's opening up, I think, the possibility of having more early warning systems in developing countries. This reduced cost of technology.
Would Laure or Irina like to comment perhaps on the geographic diversity part?
Sure. Well, as far as EQN is concerned, I think it's kind of usable everywhere. But of course you need that everyone's get a smartphone and gets it on his smartphone to be universal. So that would be probably a problem, but still some people could get the alert if enough people had it. But that also made me think about a project in Costa Rica where they also use smartphones to detect earthquakes and send earthquake early warning, but they have fixed smartphones. So they just use the accelerometers of some smartphones, but they own, the people running the project own the smartphone. So it kind of help to detect the earthquake very fast and very cheap, and then they send the alert in a more conventional way. So I think that could also be, this is still a project and under study, But I think in the future that could also be a real asset for countries, developing countries.
Yeah, I agree with both statements. And just to add one further thought, maybe it's also needed that we have a resilience assessment. So what is their culture? How do they react to other hazards, for example? Is there already an alert system for tsunamis, for example, in place? And maybe their synergies can be used between these different hazard warning systems. So it really matters regarding the cultural resilience of the different countries.
Thank you all for the detailed reply to that. I can see a few more questions. Thanks all for the presentation. Given the relatively short available lead time, I believe the reliability of such networks would be of huge value. Any thoughts regarding the redundancy of sensors, accuracy, reliance on other systems, such as mobile network towers to communicate messages? I think Laure touched a bit on that already.
Yeah, I mean, that's a tricky one. We always hope that technology will work and networks will stay strong. But yes, as long as smartphones are concerned, they may be like a network problem. So, but I mean, for the moment, I think for AQN it has never happened too much. But and I think we just need to work on that resiliency, and I don't know, I don't have like a perfect solution, I'm afraid. So yeah, of course that could be a problem. But I mean, probably if we had more cooperation between AQN who runs the app or any institution that does that and the government, so that there are like multiple ways to send the alert, that could be something. But then you would also have to be sure that everyone understands the alert and that there may be several ways. So that's a very tricky question. I'm afraid I don't have the answer yet. I don't know if Irina and Gemma, you have a better answer, but
I definitely don't have a better answer, but I just have something to add, which is that I think there's a huge challenge in earthquake early warning between being accurate and being quick. And there's a trade-off. So, you know, you can wait until you have all the data available to you and you have a very good idea of how big that earthquake will be when it comes in. But by the time you issue the alert in that case, you probably don't have any time to do anything in terms of risk mitigation. So you need to make sure that you get a good balance between the two, and it's hard to balance them. So something that we've been doing is kind of incorporating uncertainties in the algorithms into our decision-making methods that we've been developing. You know, but still, you need to have a cutoff point where you just say, okay, the information I have is reliable enough now that I need to make a decision. And if I don't make a decision, there won't be any time to take any risk mitigation action. So it's a huge challenge when it comes to earthquake early warning, definitely.
Thank you for that. Next question, a bit more broad. What are the precautionary measures to be taken in construction sites during earthquake, as there will be no tables, etc., to take cover? Or in other words, if I can rephrase that, that would be if you see a similar level of influence to an earthquake early warning system, depending on the situation that the citizens are at. If you see any difference between somebody being at home or at the workplace, and if you have identified any areas where people might be at higher risks. No identification from responses. Seems a bit outside of the scope.
Yeah, maybe a short answer here. It's again the context, because it's not the same in each country. So for example, in Switzerland, the buildings are different than in other countries, and therefore you can't say, okay, we should stay inside. Maybe it's better to run outside. So here again, the regional behavior recommendation should be considered when implementing earthquake early warning system or providing recommendations, measures.
Yeah, definitely different countries have different culture on how they deal with that. So it's also how you're trained from an early age. Next one, and a very interesting one. My name is Githin from India. I'm doing my Masters of Science in Disaster Management and Environmental Impact in France. I have a doubt in how do you act in terms of seismic misinformation and fake media coverage, and we definitely have two very well-informed people, our speakers, to talk about us. Laure or Irina, who wants to take the lead?
Well, I can start if you want. That's a very interesting question and important one, I think. With Irina, we worked specifically on that matter, and we published a communication guide. I'm sure we can put that in the chat. So there's a whole lot of recommendation on how to deal with misinformation in relation to earthquakes, and I think it is very related to our topic today because there is indeed a confusion between earthquake early warning and earthquake prediction, for example, and that can, I mean, it is a misconception that we must fight because otherwise it could add distrust toward our messages. And we really want to avoid that. So I really recommend that you go check the communication guide if you want to know more. Yes, I don't know, Irina, if you want to add a word on that.
No, perfectly summarized. I just put the link into the chat if you're interested.
Thank you for that. So we keep it definitely as an idea for a future talk, because misinformation through social media is a big deal, a big topic nowadays. So if we can get it in our context, that would be lovely. Next question. We are slightly running late, but I see only two more questions, so let's address them. Can an earthquake early warning work at least in the east and north of the city in a short time? This is for Istanbul. I think this is for Gemma to respond based on the maps.
Yeah, sure. So thanks, Murat. I mean, I haven't looked at, Istanbul in a huge amount of detail because this was a continent level wide study. I think there is an operational system in Istanbul, or there was an operational earthquake early warning system. So there is potential to definitely to have warning. The exact amount of warning that a particular location would have in the city would depend on where the earthquake occurs, how many seismic stations are located close to it, and therefore, and once you kind of understand that relationship between the seismic sensor location versus the location of the earthquake, you could actually work out how much time there would be to take an action. But it would really depend on exactly where the earthquake was and where the location of interest you're talking about is. So it's very specific. It's a very specific question to a particular earthquake.
Makes sense. And last question again for Gemma. Thank you all for the very interesting presentations. I was wondering what could be the possible ways to increase the lead time.
Yeah, thanks, Stu. So I think one of the main ways of increasing lead time is to increase seismic sensor station density. So the more stations you have, the more possibility of triggering P waves in time to actually issue an alert. Another way is if we can somehow kind of speed up the efficiency of the algorithms at translating the characteristics of the P waves into characteristics of the incoming earthquake. So they're kind of two main ways we can do it at the moment.
Perfect and clear. So I don't see any other questions in the chat, so I believe it's time for us to thank again our speakers. A big thank you, Gemma, Irina, and Laure, for your time and the wonderful presentations today. Just before we close this meeting, I wanted to share some news on behalf of SEGED. Am I sharing the screen?
Yes.
Okay, perfect. So for anyone who is interested, SEGED has launched a fund applications of up to £1,000 will be considered, and the only requirement for somebody to apply is to be a SECED member. I should emphasize that SECED membership is free for students, so anyone who is studying at the moment could apply and benefit from that. Application deadline is end of July, so please spread the word to anyone who might be interested. Thank you again, everyone. And ladies, great pleasure to have you with us today. Have a good rest of your day.
Thank you very
Thank
much.
you.
Thank you. Bye.